sessions. Okay, we need to discuss today. Okay, yeah. So again, can you hear me clearly and see my slides? Thầy bạn? Okay. So now we go to the lecture 4, part 3, and the lecture 4, part 4. Okay. Yeah. Now I just pick up some information and discuss with you. Okay. Now, now we talk about 4.6, session 4.6. So we have the important formulas right here. Yeah. So when we calculate converted power, this is 1 minus S times BAG. And of course, S is slip. Okay, BAG means air gap power. Okay, yeah. So if we have, if S is higher, that means the rotor speed lower. The rotor speed lower means converted power is lower. Okay. Yeah, remember that S higher, so converted power is lower. So if converted power is lower, that means output power is lower. And then we have efficiencies. Efficiencies is output power of input powers. So normally this one is constant, you know. So if output power is lower and this is constant, so we get efficiencies is lower. Yeah, efficiencies either is lower. Yeah, here. Yes. So that is the reason we think different ways to improve the efficiency, to get a better efficiencies. Okay. So yeah, so to do that, we think about rotor resistance. Rotor resistance. So if we have lower rotor resistance, yeah, we can increase the efficiencies, because lower resistance, that means lower rotor copper losses. And yeah, here with a lower resistance, okay, we have efficiencies. Efficiency is high, but okay, so a lower, so we have R, rotor resistance. So if rotor resistance is increase, sorry, if the rotor resistance decrease, that means we can get efficiencies is higher. Okay, because we reduce delta B RCL. That means the rotor copper loss decrease, so efficiency is higher. Yeah, look, its efficiency as normal operation condition is quite high, but when we increase, when we decrease the resistance, that means we have lower starting torque, right? Lower starting torque. So if starting torque is lower, you cannot start induction motors. Okay, yeah. So look here. If we have lower I2, you know, this is starting torque. You know, this starting torque. This one is maximum torque, or we say pull out torque, right? Pull out. Yeah. Okay. And somewhere here is the rated torque. Okay. Yeah. So of course efficiency is higher, so we think about we increase rotor resistance. Okay, here, so when we increase rotor resistance, efficiency is lower because delta B RCL is higher. Okay, but you can get a higher, starting torque, right? Yeah, higher starting torque, good starting torques. Of course we have we have the trade-off between efficiencies and starting torque. Okay, yeah, so increase rotor resistance, lower efficiency, higher starting torque. Okay, otherwise the risks are increase efficiencies but lower starting torque. Okay, look at this one. Yeah, look at this one. You can see now if R2 is higher, so now this one is maximum torque, right? Or pull out torque, and the starting torque is higher. But at this here, we have S max. Yeah, I mentioned to you before. S max mean the slip at the maximum torque. Okay, S max doesn't mean the maximum value of S. No. Okay, please remember that. Again, S max is the values of slip at the maximum torque. So here we also have, right, S max. For example, this is S max 1, this is S max 2, So this is SE0, this one is SE1, Yeah. So if we have lower resistance, we have lower S. That means efficiency rate. Okay. Now, if R2 is higher, you get lower S max. Okay, because S is approaching to 1, so we have higher S max. Higher S max, that means lower efficiency. Okay, yeah. So we need to calculate, we need to design the induction motor with suitable values of R2. Okay, so if R2 is optimal, okay, you can get higher efficiencies and higher starting torque. Okay, so we have the conclusion. So if R2 is optimal, okay, you can get good efficiencies and we get a good starting torque. Okay, yeah, so this is the ideas. So according to these ideas, they design many rotors structure, or we have many rotor designs. Okay, we have many rotor designs. Of course, we have wool rotors, and we have a squirrel cage rotor, right? Right, yeah. So yeah, according to this observation, they design many kinds of rotor. So beside that, we also consider a leakage reactance. That means we have Act2. So we think about, we have Z2E R2 plus change Act2. Okay, yeah. So now we have many induction motor rotor designs. Okay, to consider good efficiency and good starting torque. Okay, any questions, please? Thầy Bá, any questions? How about the others? We have one German student. So do you understand?
Yes, I understand.
Okay. Yeah. So continues. So here, I mentioned before, yeah, we have many squirrel cage rotor designs. Okay, later on I will tell you. Okay, so And we know for the Squirrel K rotor designs, we have a conduction bar, right? We have conduction bar, and we have shock rings. Okay, we have two shock ring, right? Yeah. So if we modify these mechanical construction, we modify the surface of conduction bar, where we will get a different rotor designs. Okay. So look, if the conduction bar of a K rotor are placed near the surface of the rotors, this is the rotors. Okay, and then if we have conduction bar, yeah, near the surface, this is surface, right? It is surface. So we will have only a small liquid flux. Okay, that's me, and the reactant X2 will be small. Okay, so X2 is small. X2 is small. On the other hand, if the rotor bar are placed deeper into the rotor surface, okay, deeper, so that means rotor bar somewhere here, yeah, very deeply. Okay, here if here rotor bar, okay, so you get X2 is increasing. Okay, yeah, so there will be more liquid, and the rotor reactance X2 is will be larger. So from here we have the ideas. So if we would like to increase R2, you get deeper conduction bar. Otherwise, if we have X2 is lower, you get the we have the bar near to the surface, Okay. Yeah. Yeah, so now we know how to control the X2, right? And yeah, for the R2, it depends on rotor bar or rotor winding, right? It depends on the construction of rotor bar or rotor winding, and X2 it depends on the position of the conduction bar. Okay, so R2, according to the material of the rotor bar or rotor winding, right? So X2, it depends on the position of conduction bar. So after that, you can get the X2 is R2 plus JX2. Okay, yeah. So continue. And here we okay, sorry, I need to reopen. So here we have some lectures coming from the professors in Frankfurt University. So it is quite interesting. So I use it. Okay, yeah, come from Professor Iris Flash at Frankfurt University. Okay, so here I mentioned before, this is the cage rotor. Okay, cage rotors, and this is conduction bar. This is conduction bar. So we have round conduction bar, deep conduction bar. Okay, tapered deep bar. We have double bar. Okay, we have the double the first one, the second one. Okay, yeah, I mentioned before we have different construction of conduction bar. So we have different X2 and R2. Okay, different. Yeah. So normally we use a round bar. Okay, because it's easy for manufacturers. Okay, for manufacturing process, because the round bar, but for deep bar or tapered deep bar or double bar, more complicated to design. Okay, that's the reason now in practice, okay, we normally see the round bar of induction motors. Okay, so for now we discuss about vector diagram. Yeah, vector diagram. vector diagram of induction motor. Okay, yeah, yeah. So here, here we have a voltage equation. Voltage equation. Okay, here U1 mean. Okay, so maybe I will draw the equivalent circuit for you. This one is R1. This one is JX1. Okay, normally we don't have RC because RC is very high. Okay, so we only consider JXM. So this one is JXM. Okay, this one is R2 over comma, right? Over S. And this one is J's X2 over comma. Okay, sometimes I use R2 over R2 from over comma S, or sometimes I say R2 R2 plus R2 over comma 1 minus S over S. Okay, it depends, but we have the same meaning, right? So here we have I2 over comma. This is I1 over, sorry, this is I1. Yeah, and we have here is V1, or sometimes we say V phase. Okay, so if we consider this circuit, and now we look at this one. Okay, this one comes from VGU lecturer. This one comes from very good lecturer. You know, the same theories, but different parameters representation, right? Okay, so we have U1 mean V1, right? Okay. Yeah, under bar means a complex number. Okay, complex parameter. So R1, right? We have I1. Okay, I1J omega L sigma 1. That's mean X1. That's mean X1. Okay, so X1 is omega L sigma 1. This is liquid inductance. Okay, so from X1, or we say X sigma 1. Okay, and we have X sigma 2 over comma is omega, right? Omega L sigma 2 over comma. Okay, or you just understand this is X1, and UQ over comma mean here. Okay, mean E2 over comma. Okay, E2 over comma. Okay, of course E2 over comma is equal to E1. Yeah, and then when we consider Kirchhoff 2 for this one, this is Kirchhoff 1, right? And so Kirchhoff 2 for loop 1, this is Kirchhoff 2 for loop 2. Okay, so we can get some you know, for this one I2 over commas R2 over commas, and then I2 over comma, you know, this is S time X2 over comma, and this is S time E2 over comma, you know, just the same, you know, because if we modify, you can get what? E2 over comma E R2 over comma S plus J x2 over comma times I2 over comma. Okay, so if I modify, you get SE2 over comma, right, equal to R2 over comma times I2 over comma plus J here S x2 over comma I2 over comma. Okay, and then we continue to modify to get this one, right? So we have 0 E I2 over comma R2 over comma, right? Plus 1 plus I2 over comma here, and then J X x2 over comma, right? And here, yeah, here is in the SA at the left side. We move to the right side, you get minus S E2 over comma. Okay, that means this equation is similar to this equation. Just modify the representation of the parameters, but actually they have the same meaning. Okay, so according to this equation, okay, they can calculate I2 over comma. Okay, yeah, I2 over comma. So this one um, for complex number. So this one for magnitude. Okay, so when we calculate magnitudes, you can get this one. Okay, yeah. So now we have two equations. We have the voltage equation at the stator, and we have the second voltage equation at the rotor. Okay, yes, yeah. And we have another equation here. Okay, why? So if here is I1, this is I1, right? And this one is I2 over comma. So this one is I0. We discussed before. So if we consider this node here and we apply a KCL, okay, Kirchhoff one, you get I1 E I0 plus I2 over comma. Okay, so here, here, here. Okay, or we can say I1 minus I2 alpha comma E I0. Of course, this is complex numbers. We forgot this one. Because if we here we have RC and then we have JXM. Yeah. So this is I0, this is IC, and this is IM. So we have this one, right? Sometimes we consider RC. So if we consider this node, we have I0 E IC, right? Plus IM. Okay, yeah. So totally we have four equations. The voltage equation at the stator, the voltage equation at the rotors, and this equation for this node, right? And we have the last equation for this node. Okay, yeah. So totally we have two voltage equation and two current equations. Yeah. Any questions? Theba, any questions? Okay. How about the others? Okay, so here we can have two voltage equation and the two current equation. Okay, so here this is stator, right? This is rotor, right? So for here we have, yeah, we have this is R1, this is one is JX1. Okay, we have I0, I mu. Sometimes we say I mu or we just say IC. Okay, IF or IFE or we say IM. Sorry, wrong. Okay, we just say here, right? Here you can get I mu, IM, and this one is IC. Okay, so we have yeah. So we have omega x LH mean XL, JXM. Okay, RFC or sometimes we say R core IC. Okay, yeah. This is R2 overcomers. So the voltage across R2 overcomers is here. R2 overcomer time I2 overcome. Okay, and then here, yeah, you get R2 overcomer time 1 time 1 minus SOS. Okay. Any questions? So here we can get the equivalent circuits according to for these equations. So it's up to you. You can follow the equivalent circuits like this. Okay, before you know, right? Yeah. You study before, or you just update some representation of parameters. Okay. Yeah, why we separate these ones? Because of this resistance is used for calculating power converters. And when you get power converters, this one we calculate rotor copper losses. So we take sum of them, we can get air gap power, because air gap power is delta B RCL over S. Okay. Any questions? So remember that we should use overcomers or we use prime, okay, for all the rotor parameters. Refer it to this data, right? Yeah. Okay. Yeah. This one's you know before, right? Okay. We analyze R2 overcomers over S is R2 overcomer plus R2 over 1 minus S over S. Okay. So we have two cases. So if S is 0, okay, so you get this ratio is approaching to infinite. So S is 0, that means you get synchronous speed. Synchronous speed. Yeah. Synchronous speed. And S is 1, you get stationary, right? Stationary, that means rotors is blocked. Okay, rotor is stationary as it's 1. Okay, so if S is 1, you get this one is approaching to 0. Okay, I mean this ratio is approach to 0. So we only have R2 prime. Okay, yeah. So we need to draw the phasor diagram. Okay, again, you need to look back the equivalent circuit. Okay, we have rotor parameters refer it to stator. We have stator parameters. We have two voltage equation, two current equation. So remember that when you draw the vector diagram of equivalent circuits of induction motors, you start at phi x. What does this mean, phi x? Phi x mean air gap flux, air gap flux, or we say main flux. Okay, yeah. And before, here is x-axis, right? X-axis. So I mu come from here. Okay, so this is phi x. This is phi x. Yeah. So we know before I and phi. I mean I mu equal to I0 because this is I0. Yeah. So the same direction with air gap flux. Okay, so you get this one. So we have the voltage here. The voltage here we say UQ, or we say U2 overcomer. Okay, and you also remember that. Okay, so if we have E and phase, okay, this is internal voltage, this is magnetic flux. So E always perpendicular to phi, 90 degree, right? 90 degree perpendicular. And we know the is leading to phi x, to phi 90 degrees. So if here phi x here is UQ or E2 overcomer, right? So here you get minus. Okay, here you get minus E2 overcomer. Why you need minus? Because here we have minus. Okay, so here you get positive UQ primer. Okay, I've got a primer. Okay, primer. Okay, so here we have a minus. So at the bottom, at the top. Okay, so this is I2. This is I2 overcomer. This is I2. So that means I1 E, I0, right? Here, if we consider this knot, so I1 is I0 plus I2 overcomer. So here, this is I2 overcomer. So you can get I1. Yeah, you can get I1. Yeah, you can get I1. So if we translate I2 overcomer from here to here, okay, so what is this? This is theta r. That means this is the phase angle. Theta r is what? Theta r is what? Sorry, I need to keep and open again. Okay, so we know theta r is what? Theta r is the phase angle between E2 overcomer, between E2 overcomer and I2 overcomer. Okay, so you can get cosine theta r. This is the power factors of the rotor. Okay, here. Okay, now I1. Look, this is I1. Okay, so continue. So now we know for minus I2 overcomer. This is I2 overcomer, right? Okay, so here, this is UQ overcomer. This is I1, right? I1 times R1, you can get this factor. And now this one is I1 times J X1. Okay, so you get here is U1. Here is U1. Okay, here U1. And here U1, here I1, so this phase angle is theta s. Because we know theta s is the phase angle between U1 or V1, right? Or V phase, right? With I1. Okay, so this is the theta s. Yeah. So now the second voltage equation. Yeah. This one is 0. This one is 0, right? 0. Plus, okay. Oh, something wrong. Let me check. Okay. So from we have I2 over commas I2 from over S here. Okay, plus this one. Okay, so equal to UQ, because if we move UQ here, okay, you get UQ over comma is this one plus this one. Okay, here. Yeah, finish. So this is the phasor diagram of this equivalent circuit. Okay, any questions, please? So for the final exams, we just unify x-axis, right? Okay, x-axis is for I mu or I am. Okay, I am. Or we just say I am equal to, sorry, it is in the same direction with phi x. Any questions? Thế Bá, any questions? Other, please. Okay, yeah. So we finished this one just for your reference. Okay, yeah. Okay, just some modifications of equivalent circuit. Okay. So yes, okay, yes, got it. Okay, okay. Okay. So come back. Okay, so now we come back to different we have different cage rotor design. Okay, so now according to the standard, we have 4 classes of cage rotor designs. Okay, rotor designs. Okay, class A, class B, class D, class C. Okay, so different rotor designs. Remember this one for cage, Kiro, Skiro, cage rotor design. Okay, for class A. So just we have some key difference between different kinds of rotor designs, K rotor. So for class A, or class A, yeah, we get very good efficiency. Okay, class A and class B is very good efficient, but the starting torque is lower, right? So for class C, yeah, very good efficiency and also very good starting torque, right? Yeah, very good starting torque because starting torque is high and efficiency is high. Efficiency is high because S is small. Okay, because S is small. So now class D, for class D, we get very high starting torque, but efficiency is not good. Efficiency is lower because the slip is higher. Okay, so it depends on the application. We can use class A slash B, class A slash D. Okay, sometimes we need very high starting torque, right? Yeah, sometimes we need very high starting torque. Sometimes we don't need to get more starting torque. We should need higher efficiency, so we can choose class A, class B. Okay, so for the trade-off between the starting torque and efficiency, we choose classes. Okay. So for how can we know for class A's, class B's, or class C, class D, you consider this figure. Okay, this is class A. For class A, you can see the rotor bar here. The rotor bar here. That's mean very near the surface. Okay, the conduction bar or rotor bar very near the surface. Okay, so X2 is very small. Okay, so class B, here we get very deep. Okay, very deep conduction bar. Okay, so X2 is higher. So for class C, this one is this is near your deep rotor bar. Okay, for class C, you can see this is double cage rotor design. Why? Because here we have this. We have the first stage of conduction bar, and we have the second stage. Okay, of the conduction bar. So we have two. Yeah. We have two stage. Okay, so the first stage here and the second stage here. Okay, yeah, class C. So class C is very good. Class C is very good now. I mean, the double cage rotor designs are very common for high power induction motors. Okay, now we have D. Okay, we have very small bar near okay, sorry. So very near the surface, very small, very small conduction bar area. I mean cross area and near the surface. Okay, so that's the reason for class D. We get very high starting torque, but lower efficiency. Okay, yeah. Any questions? Female students, Xuân Quỳnh, any question, Xuân Quỳnh? Rồi nó nghỉ học rồi.
I don't have any question.
Okay, thank you. Okay, so so now here we have some description, right? we have some description of class D. This is class D. Okay, and here we have some description. You study, yeah, you read for yourself. Okay, look, because this is near the surface, so H2 is very small. Look, okay, the rotor liquid reactance is still small. Okay, this is yeah, this is double cage rotor designs. Okay, double cage rotor design. So we have, for example, here at the top of bar, at the top of conduction bar, and this one is at the bottom, at the top, right? At the bottom, of conduction bar. Okay, so here we can get equivalent circuit. This is slip rings or shock ring, right? Shock ring. Okay, we have the same resistance, but L here, L1, L2, L3. Okay, so L at the top, okay, and L3 at the bottom. Okay, yeah. So you can see at the top, L very small, L very small. Why? Because X2 is small. That means X2 is omega L2. Okay, so this is small, so this one is small. Okay, and at the bottom, more L3. Okay, so now we have the conclusion: L3 higher than L2, higher than L1, higher than L. Okay, this is the bottom. The bottom side, and this one is the top side. Okay, any questions? Okay, so yeah, we have more descriptions, and yeah, you read for yourself. Yeah, okay, self-study is good. And this is class C, double cage rotors. Okay, yeah, and this is the summary. We have class B, class C, class D. For class D, very high starting torque, but efficiency is low. Okay, class D, starting torque is very high, but efficiency is lower. Okay, and yes, we finish session 4.6. Okay, we have examples of very easy example. So you read for yourself at home. Okay, yeah. 4.7 for your reference. Okay, we have some trends in the industrial motor designs. Okay, so when you read number 1, number 2, number 3, number 4, number 5, number 6, you can understand what is the next generation of motor designs, industrial motor designs. For example, here we need more coppers in use in the stator winding to reduce the copper losses. Okay, the rotor and the stator core length is increased to reduce the magnetic flux density in the air gap of the machine. That means, nowadays, every industrial motors, yeah, we have very long length. The induction motors, the radius is small, but the length of induction motors is longer. Because if we lengthen the size of the motors, you can reduce this magnetic flux density in the air gap. Okay, that means more magnetic flux, okay, from the stator come to the rotors. I mean magnetic flux. Okay, so more steel is used in the stator of the machines, allowing a greater amount of heat transfer. Okay, more steels, so we can operate the induction machine in induction motors with higher temperatures. Okay, yeah, so more heat transfer, so we can reduce these operation temperatures of induction motors. Okay, what else? Okay, and so on. Okay, so when you read this slide, you can understand so what is the next generation of induction motor design. Okay, yeah. For sessions 4.8, we skip. Okay, how to start induction motors. Okay, you can read my lectures. You can understand. Okay, and remember that here we have all formulas summarized by me. Okay, and it will help you to answer the homework. Also for the final exams in relation to induction motors. Okay, yeah. Okay, so we skip 4.8, and here at this slide 63, we have a guideline for lab sessions, and of course, Mr. Hill uh, will cover the lab activities. But so when you read this slide, you can understand mm, why we do the lab lessons for synchronous machine or induction machines. Okay, yeah, and yeah, we have for example, for the final exams, I give you this device, and I tell you, I ask you, what is the main function, okay, of that device? Okay, so you need to tell us, you need to tell me, what is the main function of this device? Okay, here we have switch, here we have circuit breaker, here we use uh, relay, okay, or protective device, and blah 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 blah. Okay, so you need to tell me what is it and why we use it. Of course, this is the three-phase supply unit with circuit breaker. This is circuit breakers. Okay, and what is X? Okay, yeah, what is X and why we use this one? We use for what? Okay, this is control unit, right? Okay, so we have two operation modes. Okay, so the first one is motor mode, motor operation mode, and current, sorry, and generation mode. Okay, so if here you see if this line, sorry. So if this lies, if this light is turned on, that means we are doing the motor operation, right? So if this light is off, that means we operate at the generation mode. Look here, you know, we open, right? We start, we press the star for some times, okay, and then you can see the light is turned off, okay, and this is operation mode. Otherwise, when you leave the star, that means you don't press the star when you open the switch, okay. This control unit operate at the motor operation mode. Okay, I think all of you understand because you already did the lab sessions. Okay, of this course. Okay, and I will ask you, what's a this circuit? Okay, and we use this circuit for what? We use this diagram to do what? Okay, or I will ask you what is X and why we use DC power supply, you know? Yeah, of course, we use a DC power supply to supply the voltage and current into rotor winding of the synchronous machine, right? Yeah, so if we have IDC or we have IR rotor current, yeah, we can generate rotor magnetic field. And if we have phi S, okay, versus phi R, you can get induced torque, right? Yeah, we discuss, yeah, the theory about this one. Or we have PS, okay, cross B, BR, okay. Yeah, K, you can get induced torque. Sorry, KBR, right? KBR, yeah, KBR cross BS. Okay, so for what is circuits? Okay, why we need to measure voltage? Why you need to measure current here? Voltage, currents, power factors. Okay, yeah, many. Okay, so this is the ideas in relation to lab activities. I will add that information into the final exam. Okay, yeah, this is A1, and yeah, of course, we also mentioned about V curve. Yeah, for synchronous motors, we also discussion about V curve, right? V curve. This is V curve. V curve show us the relationship between IA and IF, right? IA and IF. This is IF. This is IA. Okay. Yeah. For different power. For different power. Yeah, this is V curve. Okay. And for the final exams, I also yeah, sometimes some in text I will ask the student what is the meaning of V curve. Okay. Yeah. Okay, this one for synchronous generators. Okay, synchronous generator, how can we make the synchronization process? You know, yeah, this is a synchronization process. Synchronization process. Okay, so yeah, if you've attend really my classes, okay, you can know what is this, right? This is synchronization unit. Okay, so here you can see this session to observe the frequency, right? The frequency. So if we have F1 equal to F2, or we have synchronous generator frequencies equal to read frequencies, right? Okay, we can turn this switch, okay, from off to on, right? Okay, so here to observe the frequencies. Here we observe the voltage. Here we observe the voltage, and we observe the voltage and the frequencies. We observe the value of voltage, the value of frequencies, and the sequence. Yeah, also I mean phase sequence. Yeah, and phase angle. Okay, so here we have the same voltage, the same frequency, and this light turn on, right? You switch on this device, and the synchronous generator will connect to the grid. Okay, yeah. How many students finished this experiment? Thầy Ba, are you finished for this experiment? Okay, yeah, maybe some students, yeah, they have already finished this experiment. Okay, yeah, here, you know, yeah, that's what I mentioned here. Okay, this is voltage, frequency, this is width. Okay, this is delta U. Of course, you should make sure delta U is zero, you know, is zero here. Yeah. Okay, and the ring LED is turned on. Okay, we can switch from 0 position to 1 position. Okay, yeah. Okay, we measure power factors. Okay, now we come to the asynchronous induction machine. Okay, so we have slip rings induction motors, and we have a squirrel cage. Okay, slip ring means the slip ring means wool rotor, right? Right. Sometimes we say slip ring, sometimes we use wood rotor induction motors. And the second one, of course, this is squirrel cage. This is squirrel cage induction motors. Yes. Yeah, and please review it. Yeah, review it. Okay, this is for slip ring and squirrel cage induction motors. Okay, of course, Mr. Hill also share with you about the lab materials. Okay, before you do the experiment. Okay, so yeah, we finished lecture 3, lecture 4, part 3. Now we take a break 10 minutes, and we will come back to study lecture 4, part 4. Thank you very much. See you later. 2:45 p.m. Okay.